and Professor Max Niu will tell us about stacks and monads.
Hi, yeah, I'm Max, University of Michigan, and this is my joint work with my PhD student, Yuchen, and former undergrad, Runze, who's starting at Indiana this semester. Okay, so this talk is about implementation of effects in our programming languages. So things like exceptions, mutable state, and continuation effects, right? And if I ask you, okay, how am I going to program with these effects in my programming language? Well, it depends on the setting, right? So on the one hand, we have how we abstract over effects in our high-level programming languages, things like Haskell, Scala, OOPSLA', right? And for that, we know that due to the great work of Moji and Wadler in the 80s and 90s, we can use monads, right? So what is a monad, right? Monad takes a type A and gives you a type TA that we think of as the type of effectful programs that return A values. And the monad interface gives you the most basic operations that such an effect should support. So we can embed pure values using return, and we can sequence with a kind of let binding, which we use with do notation. Okay? And then we can instantiate all this with different effect implementations within our language to kind of virtualize these effects, to add them to a language that doesn't already have them. Okay? So, on the other hand, ICFP is over, and now we're at OOPSLA', okay? So, so rather, we'd probably say, I'm going to just have those effects in my programming language already, and I'm going to implement those effects in my compiler, right? So what does that look like? Well, it doesn't look that different, but it's a little lower level, right? So as an example, let's look at 3 different ways that we can implement exceptions in the compiler for a language that has them, right? So on the one hand, we could do something very similar to what we might do with the either monad, which is we have a continuation which says either I'm a successful value A or I'm an error value E, right? And then I'll have the continuation, the caller stack frames below that. Okay, on the other hand, that's not actually very efficient. There's too much branching on these data values, so a more efficient one is to have 2 different continuations, one for success, one for exceptions, and then I don't have to match on the result. Okay, and then even we have more complicated things like the way we have exceptions in C++, where we have markers on the stack to determine which exception handler to run, and when I raise the exception, I actually have to traverse the entire stack. I need to know how the entire stack is structured in order to implement this, right? So the question I have is, that we address in this work is, what's the relationship between these 2 problems, right? Or to these 2 approaches, right? So on the one hand, we know that we can abstract effects in high-level languages, virtualize effects using monads, but when we compile them, we have these more low-level ideas of stack manipulation, and we're designing the structure of the stacks. So the question that we address is, what fills in the blank here, okay? And the solution we have is what we call a relative monad. Okay, so contributions of our paper is we adapt this existing category theoretic notion of a relative monad to a call by push value language to talk about abstraction over low-level effects. And then we introduce a kind of extension of do notation for those relative monads. And as an application of that, we show that unlike ordinary monads, we can automatically derive relative monad transformers, so we can build up more complex effectful languages from small components. Okay, so first let's talk about the formal setting that we use, which is called call by push value. And for the purposes of this talk, I like to just think of call by push value as a domain-specific language for working with stack machines. Okay, so call by push value introduces a kind distinction for different types. So on the one hand, we have value types, which are the kind of types we're used to in call by value languages. So that's basic data types, tuples, tagged unions, and closures. And we might, and recursive ones, we have recursive data types like our favorite linked lists. And on the other side, we have the computation types. And the way I like to think of these is these are compositionally describing the structure of the runtime stack. So we have a function type, which we think of as describing arguments passed on the stack. We have products, which we think of as encoding destructor tags that are placed onto the stack. the returning type A, which is the continuations that are implemented on the stack, and we have polymorphism as well. And the recursive version of this is we have co-data types. So for example, we can implement a stack-based implementation of a multi-argument function this way. Okay? So how would you do it, right? If you were just a programmer working in call by push value, what would you come up with for monads? You wouldn't come up with the usual notion. Okay? And the reason is that the notion of monad you would naturally come up with isn't a monad because it changes the kind of the types. So an ordinary monad takes a value type and it gives you the same kind of type out. It also gives you a value type, right? Which says that it's a first class value in the system. But when you work in this lower level setting, it changes the kind. It says I take in a value type and I return to you the type of the stacks for computations that perform the effects, right? And so if we're thinking about these computation types as a stack, I can directly express these kind of stack implementation strategies that we saw before. Okay? And this is not a monad because it's not even an endofunctor. And fortunately, there was a paper, Monads Need Not Be Endofunctors. And it turned out that this implementation that we came up with in call by push value exactly fit into this relative monad setting. Okay, so what does the interface look like, right? We have a TA and it changes the kind. Well, the great thing is it's exactly the same, okay? Exactly the same interface, we just have return and bind. The only difference here is that the TA is a computation type rather than a value type, right? So it very easily generalizes everything that we had before, and we can implement all of our favorite monads that we have in high-level languages. But what else can we do? We can also go and implement these low-level view of these exception monads. So the first example here, the one from Haskell, we only need to modify it by introducing the fact that this actually returns a value of A plus E rather than just being A plus E. On the other hand, we can use a kind of church encoding to express these multi-continuation implementations. So we take in two continuations, and here the important part is that this R that we're quantifying over is itself actually one of these computation types and not a value type. And it's a bit hard to read, but we can use the recursive code data types to express these complex stack structures, and you can actually implement the stack walking and finding the correct exception handler just as a normal recursive stack manipulating function. Okay, so that's relative monad. So what then did we do with it? So the most familiar thing to do with monads is we get a nice embedded programming language, which is the do notation. Okay, so in a high-level language, and this goes back to the very original paper from Eugenio Moji on monads. He proved a theorem which said, if I have a monad on a model of pure lambda calculus, I get a model of call by value lambda calculus. And that corresponds to a syntactic translation, which is I can embed a call by value programming language, I can translate it into a pure programming language if I have a monad. And this is really just desugaring the do notation. Okay, so what does this look like in call by push value? Well, we get something even better. Okay, so unlike the previous case where we're translating from a pure from an effectful language into a pure language, the difference in call by push value is we actually are translating from call by push value to itself. So given a monad, a relative monad in call by push value, we can do a generalized do notation translation that we call monadic blocks. And you can even iterate this and combine effects together in this way. And so we have a corresponding generalization of this theorem that we call the fundamental theorem of call by push value relative monads. And the details of that are all in the paper. Okay, and so it's a fairly straightforward generalization of do notation, but we have to do some type-directed stuff. But other than that, it looks very much like a kind of do notation you see. You map from the do's to binds of your monad. But you also need to do something for all the things that are not just returning values. Okay, and we call it the algebra translation. Okay, and then as a last example, what do we do with this monadic blocks? well, we're actually able to automatically derive relative monad transformers. Okay, so what are monad transformers? Well, these are a common tool in high-level language for constructing complicated monads from smaller components, right? And a monad transformer takes in a monad and it spits out another monad that we think of as adding some new effects, right? And so by composing these together, we can get complicated monads, right? And in high-level languages like Haskell, we know that given a monad transformer, you can apply it to the identity monad to get out an ordinary monad, but the other process is not automatic. It takes some ingenuity to figure out what that monad transformer should be, and it turns out that not every monad even has a corresponding monad transformer. Okay? But we saw that this self-translation that we get in the algebra translation did give us a way to combine effects together. And so it turns out that actually relative monads compose for totally free. And I want to give some intuition for why that is. So let's take a look at a state monad. So a stack for a state monad, let's say we store the state at the top of the stack, right? And what happens is we always, in call by push value, have to have a tail of the stack that's owned by the caller, right? That we're not allowed to touch. And the idea is that this fact that we're polymorphic over the tail of the stack is exactly what lets us compose, because we can store our other effects higher up on the stack that we're polymorphic with respect to. Okay? So if that caller happened to be an exception monad, we would get for totally free a combination of state and exception effects. Okay? So relative monads, in a sense, are always polymorphic over this tail of the stack, and that's why we get this compositionality for free intuitively. Formally, the way we can do it is to use our algebra translation. So what we can do is we can take our implementation of one monad and apply it to the algebra translation for another monad, and we get out the transformed monad. And so if you do this with an abstract input monad, you get out the monad transformer. And so this is a completely automatic process. Yeah. Okay. So there's a lot more details in the paper, including laws of relative monads and formal definition of the algebras and the algebra translation, and a proof that the resulting monad transformers are law-abiding as well, in addition to detailed descriptions of various monad examples and how they adapt to call by push value. All of this is implemented in our research language based on polymorphic call by push value that we call Zydeco, and the artifact is available for that. As far as future work, currently Zydeco is not compiled. We have a stack machine-based interpreter, and so we have stacks we can look at, but what we really would like to do is to implement these efficiently and see if we can use techniques like this one to get performant and correct compilers a la carte. And as an additional, when you do any category theory, you have to think about the dual setting, and so I'm very curious about what a relative comonad construction might look like for a language as well. Okay, that's my talk. Our three main contributions: we adapt relative monads to the call by push value setting, so we get a lower level view of effects. We introduce the monadic blocks to generalize do notation, and we use that to derive relative monad transformers for totally free. Thank you.
Thanks, Max. This seems great, but you didn't talk about the limitations. How is it to program with your language? Are there any sort of pain points you've encountered so far?
So you just mean programming in call by push value?
Yeah.
As a programmer? Yeah, certainly. So it's very similar to working in CPS, I would say. So I'd say it's a fairly low-level programming language. So I'm more thinking of it as something you would use as a target language, but I know I've also gotten pretty good at programming.
What would you imagine having as your source language then? Oh,
well, you could have a call by value language to start with. You can just have off-the-shelf call by value, call by name. But I do think there are features that are informed by this call by push value structure that we could maybe add to the source languages.
I'm specifically thinking, can you benefit from the fact that you have this composability of relative monads at
Yeah.
the level of the source language?
I don't have concrete proposals, but I think I would hope so. Yes.
Okay. Thanks.
Hi, very nice talk. I wondered, is it allowed for the monad operations to be internally use effects of another monad in this language?
You mean when we use this monadic blocks?
Mm-hmm.
Yeah, so not for free. What you get for free is anything that's closed you can lift like this. But you can basically, we have some syntax sugar that we've proposed. And basically you can parameterize the block by those operations. So it's not very nice to use right now, but you can do it. And we think with some good language design, it could be more ergonomic.
Thanks.
Hi. Could you go to slide 9, please?
Sure.
No. Oh, yes. Here. Beautiful.
Mm-hmm.
On the left-hand side, you have a plus and times, right? That's
Yes.
great. And on the right-hand side, you have ampersand, which is
Yeah.
with. What about par?
So the duality here is the plus corresponds to the with and the times corresponds to the arrow.
And a more symmetric par, could you speculate what that would mean in terms of stacks?
No.
Okay.
So the thing I'll say about this is it's very important that our computation types are second class in the system, which means that we can implement these as a mutably updated stack in place. Classical stuff, classical linear logic stuff, I don't know.
Okay, thanks.
Thanks all the speakers in this session, and it's lunchtime.